Okay, let's get started on the homework for the week. Okay, number 1, find the vector parametric equations for the line passing through the point P, which is 4 minus 2, 1, and perpendicular to the plane 5x plus 3y plus 7z equals, plus 6 equals 0. Okay, so if we have a plane, we want the equation of the line that is perpendicular to this and goes straight through. That's an awful drawing. So if we have a plane, let's go like this. We have some point, then our line is going to go at 90 degrees to this. And off in the other direction as well. Okay, so for this, the direction that it's going in to be perpendicular to everything in the plane, well, the vector that's perpendicular to everything in the plane is just the normal vector for this plane. And the normal is just going to be 5, 3, 7. Okay, so we have our direction vector, right? It's in the direction of the normal. We have our point, so we can write the line x, y, z equals, so I have 5, 3, 7 t plus 4 minus 2, 1. Okay, so it says to give the vector parametric equations. So we want to give this in parametric form. So let me go ahead and write it this way. Y of t, z of t equals, well, so if I just distribute this all out, what I get is 5t plus 4, 3t minus 2, 7t plus 1. And this should be enough, but if you want to be a little bit more explicit, you can write x of t equals 5t plus 4, y of t equals 3t minus 2, and z of t equals 7t plus 1. And that's my answer. Okay, number 2. Find the distance from the point P, which is 1, 3, 4, to the line R of t, which is 3 I hat plus j hat plus 2k hat plus t times 3I hat minus 4k hat. Okay, so the first thing I'm going to do is right away I'm just going to write this in component form. So this is 3, 1, 2 plus t times 3, 0 minus 4. That just makes everything a lot easier to work with. Okay, so we have a point and we have a line. We know a point on this line, and we know the direction vector. Right, so this is P. This is going to be 3, 1, 2, right? That's our point on the line, and then this is our direction vector. Okay, and I'm looking for this distance right here. So what I'm going to do is I'm going to make this vector right here, and then I'm going to do the projection onto this vector. And that's going to give me, let's see, color. That's going to give me this vector. So I do the projection of this onto the direction vector, and that's going to give me this red vector. And then the result that I want, I'll put in blue. The result that I want is the length of this vector. Okay, so I'll get this by just doing this long vector minus this long vector on the hypotenuse minus the side that we just found, minus the projection. Okay, so first I make this vector right here. Okay, so that's going to be, I'll call this Q. So the vector QP, it's going to be P minus this 3, 1, 2. So that's 1 minus 3, that's minus 2. 3 minus 1, that's 2. And 4 minus 2, that's 2. Okay, so this is our vector right here. Now I do the projection of this onto my direction vector. Okay, so if this is D, this is Q. Okay, so then the projection of QP onto D, right, that's going to be this red vector, is QP dot D over norm D squared times D. Okay, so QP dot D, so that's going to be minus 2 times 3, minus 2 times 3, that's minus 6, and then minus 8 over 3 squared plus 4 squared, that's going to be 5 on the bottom, no, 25 on the bottom, times the vector 3, 0, minus 4. So that's the vector minus, what, minus 14 over 25, 3, 0, minus 4. Okay, so then I can distribute that out if I want. So this would be, so this is going to be minus, what, 30, 42 over 25, 0, and then 40, 52, 56 over 25. Okay, so I'm almost done. That's this red vector right here. Okay, I need to do this long vector, PQ or QP, QP minus the projection of QP onto D. And that result is going to be this right here, this blue vector. So if I do QP minus the projection this is going to give me, so I have minus 2, I'll write this as 50 over 25. 50 over 25. So I'm doing, so it should be minus 50 minus 42 over 25. Okay, then I do 2 minus 0. And then again, I'll do 50 over 25 minus 56 over 25. Okay, So I simplify this and I have minus 8 over 25, 2, and then minus 6 over 25. Okay, let me add a page. Okay, so this vector that we just found, this was this blue vector, right? That's the vector we're looking for. Now all we need is just the length of that vector. So what we're looking for is the length of QP minus the projection onto D of QP. Right, that's what we're looking for. Okay, so I have square root of 8 over 25 squared plus 50 over 25 squared plus 6 over 25 squared. Okay, so I just need to simplify this and then I'm done. So this becomes, well, I can factor out 25 squared from each of the denominators. Now if I bring that outside of the square root, it loses that square. So I'm going to have 1 over 25 square root 8 squared plus 50 squared plus 6 squared. 1 over 25 square root, that's 64, plus 2500 plus 36 square root, 36 and 64 is 100, so this is 2600. And that can simplify a little bit. That's equal to 10 root 26 over 25. The 5 and the 5 cancel, so we get a 2 over 5. So we get 2 root 26 over 5. So again, how did I do this? To recap, I did the projection of this QP, which I was able to find because I knew what Q was. It was on the line. I did the projection of this onto the direction vector, and then I found the complement of that, the orthogonal complement, by doing QP minus the projection. Finally, I took the norm of that, and that's how I got my answer. Number 3. Find an equation for the plane that contains the points P, which is minus 1, 3, 6, Q, which is 1, 2, 4, and R, which is 3, 6, 6. Okay, so I'm going to make the vectors PQ, which is, so that's Q minus P, so that's 1 minus minus 1, that's 2, 2 minus 3, that's minus 1, 4 minus 6, that's minus 2, and then the vector PR. That's going to be 3 minus minus 1, that's 4, 6 minus 3 is 3, and 0. Okay, so to get the normal for the plane, so both of these vectors right here lie in the plane, okay? So if here's these 3 points, I found PQ and PR, right? So they're both going to be flat on the plane, flat on the screen, and the normal to the screen is going to be sticking straight up out, right? So that's the way I get that is I need a vector that is orthogonal to everything in the plane, right? It's going to be orthogonal to PQ and orthogonal to PR. Well, we have an easy way to generate that. We do PQ cross PR. Okay, so let's start computing. Do I, J, K plus minus plus PQ is 2 minus 1 minus 2, 4, 3, 0. Okay, so this is going to be, so I cross out that row. I have 0 minus minus 6. I have positive 6. Minus j hat. So I cross out the middle row. I have 0 minus minus 8. I have 8. Finally, I have k hat. So I cross out this last row. I have 6 minus minus 4. 6 minus minus minus, let's see, 6 minus minus 4. So this gives me 6 minus 8 and 10. Okay, so the point of that was to get the direction vector for this plane. Now that we have the direction vector, we need a point on the plane. Well, we know that the point passes through P, Q, and R. So I could pick any single one of these, and it would give me the equation for the same plane. Okay, so now that I have the normal, I'm going to do n dot x, y, z, right? And this is going to be my normal. So n dot xyz is going to be equal to n dot whatever point I pick. Okay, so I'll choose P just because it was first. It could have been any one of those three. Okay, so now I'm going to go ahead and distribute this. So I have 6x minus 8y plus 10z equals, so n dot p, I have minus 6 minus 24 plus 60. Okay, so this on this side is going to simplify to that's minus 30, so this is going to be 30. So my final answer is 6x minus 8y plus 10z equals 30. Number 4. Find the distance from the point P, which is 5, 2, 3, to the plane x minus 2y plus 2z plus 3 equals 0. Okay, so this is a bit simpler than the previous one. Okay, so here we have a plane and we have a point. Let's put it right here. So we have something sticking up here, and we want to find the distance to the plane. Well, the distance is going to be, the shortest distance is going to be when we just go straight up out of the plane straight to the point. Like straight up out of the plane like this, right? All the way up to the point. And this vector right here, the one that sticks straight up out of the plane, is exactly the normal vector, right? So this is going to be the normal vector. This is our point that we're interested in, and this needs to be some other point on the plane. I don't really care what. Okay, so if you forgot the formula, the way you would do this is just take any other point on the plane, pick a point, pick an x, pick a y, figure out z, and figure out this vector, right? You just figure out the vector qp, and then you do the projection, or the component, of qp in the direction of n. qp in the direction of n, and that's going to give you exactly this length right here. If we do that though, we get this following formula. Okay, and this formula is exactly just the exactly what I just said, the projection or the component of this onto here. All right, so this is going to be n dot p. Actually, let me write it. Let me just write the full formula. So I'm going to have ax plus by plus cz plus d over square root a squared plus b squared plus c squared. So on the bottom, this is the norm of the normal. Okay, these first 3 points, this is n dot p, right, the point that we're interested in, and this, right, that's going to be this right here. That's going to be n dot whatever point we had on the plane. Okay, so this is easy enough to fill in. I have my normal, which is 1 minus 2, 2. So n dot p on top, that's going to be 5 minus 10 plus 6. That's not minus 10, that's minus 4. Right, 5 minus 4 plus 6 plus 3 over the norm of this vector, and that's going to be 3. So here we have absolute value of, that's going to be 1 plus 9 over 3, so this is 10 over 3. And the absolute values are just to make sure we get a positive value. If we would have gotten a negative, you can just flip the sign and make it positive. Okay, page append. Okay, so number 5. Find the volume of the parallelepiped that has one vertex at 0, 0, 0, which has edges given by A, which is 2 minus 1 minus 2. And I'm translating this right away into component form. B, which is 3, 4, 0. And C, which is 4, 0, 3. Right, 3, 4, 0, 0, 4, 0, 3. Okay, so the way we do this, it's simple enough. It's just going to be A dot B cross C. So let's start computing. Minus 2. This is 3, 4, 0, 4, 0, 3. Okay, so I have 2, right, so that's the 2, times 4 times 3, which is 12, minus 0. Minus, right, remember I still have plus, minus, plus. So minus, across the middle out, I have 9 3 times 3 is 9 minus 0. I think I made a mistake in on Wednesday when I did this in class. Plus, no, that's minus. Okay, hold on, I forgot a minus here. So we have minus here, right, so I do minus 1 times 9 minus 0. Okay, plus minus 2 times, so I cross this one out, 0 minus 16. So if you're studying for this test, make sure you're extra careful with your signs when you're computing these. 24, so this is going to be 9, negative 9, positive 9. Here we have negative 16, positive 32. So that's 5665. Okay. 6. Find the unit normal vector to the plane with equation 5x minus 13y plus 12z plus 4 equals 0. Okay, well, we can write the normal right away. This is going to be 5 minus 13, 12. And then the norm of n, that's going to be square root of 25 plus 269, I believe. No, 169. And plus 144. Okay, so 169 plus 169, right? Yeah. So that's just going to be 13 root 2. Okay, so finally we write our unit normal vector, which is going to be 5 over 13 root 2 minus 1 over root 2 and 12 over 13 root 2. Okay, number 7, 2 more. Find the cosine of the dihedral angle between the planes 3x minus 4y plus 6 equals 0. Okay. And the plane x plus 2y minus 2z plus 10 equals 0. That is, yes, a minus 2z. Okay, so in this one, n1 is going to be, the normal for this plane is 3 minus 4, 0. And in this one, n2 is going to be 1, 2, minus 2. Okay, so we just need to find the cosine of the angle. We don't need to find the actual angle, but we know that the cosine between two planes is the same as the cosine between the two normal vectors. So that's going to be n1 dot n2 over norm n1 norm n2. So n1 dot n2, that's going to be 3 minus 8 over, that's going to have a norm of 5, and that's going to have a norm of 3. Right, 3 squared plus 4 squared is 25, and then 1 plus 4 is 9. So this is minus 5 over 5 times 3, which is negative 1/3. Right, we're not looking for the angle, we just want the cosine of the angle. Final question. Find a vector function that traces the circle in the xy plane with center 7, minus 3, and a radius of 2. So the center is going to be x minus 7, and, squared, plus y minus minus 3 squared equals 2 squared, right? And the radius is 2. Okay, so if I divide everything by 2 squared, what I end up with is x minus 7 over 2 all squared plus y plus 3 over 2 all squared equals 1. So I have something squared plus something squared equals 1. This should remind you of sine squared plus cosine squared. So I'm going to set this equal to cosine and set this equal to sine. So I have cosine t is x minus 7 over 2, and sine of t is y plus 3 over 2. So finally, I solve for x, so I have x of t is 7 plus 2 cosine of t, and I solve for y, and I have y equals minus 3 plus 2 sine of t. Now, it doesn't really say if, it just says in the xy plane. It doesn't say if we're talking about 3D space or 2D space. So if I needed an extra one to be in the xy plane, and we're talking about 3D, then I could also always include z of t is just 0, right? And that would be the xy plane, but in three-dimensional space. I think it would really be fine either way. All right, so that's all for homework number 3.